All right, welcome back. Part 2, SysTick timer. So just before we go into the pulse width modulation, I just wanted to clarify with this, this load. So if I wanted to wait, so this is creating a wait 1 microsecond counter, counter with delay coming in. And so remember, each time the SysTick ticks, it takes 20.83 nanoseconds. We saw that up here. Just double check, 28.83. So that's that 1 over 48 e to the 6. Because each time it ticks, the clock is ticking, it takes 20.83 nanoseconds because it's clicking at the rate of the clock, which is 48 megahertz. So if I take that 20.83 nanoseconds times 48, what I get is about 999.84 nanoseconds, which is just about 1 microsecond. And that's allowing me then to do that delay there for 1 microsecond. So I just wanted to clarify, make sure everyone was tracking. This math is going to come up quite often. And I might on a GR say, hey, how do I create a 10 microsecond counter? And you just need to know that it all comes down to this 20.83 nanoseconds because every tick of the clock is 20.83 nanoseconds. And I just manipulate that by creating, this internal wait. It's going to wait a certain number of already where I'm going to load in a delay value, or that's going to manipulate that so you can get to this value that we'd like. So this is the math that we need, and the way we do it is now you would put the general form of the equation then would be, I'll put another star, 20.83 nanoseconds times our load value equals whatever goal delay. So I'm not going to write delay because that's going to get confusing, but say here 10 microseconds. And then we solve for load, and then that's going to be what goes into here. And then this delay allows us to manipulate that. Say I want to wait, 110 microseconds or anything along those lines. All right, let's move on to pulse width modulation. So we can use these timers to create these pulses. Think of it just right here, as this example shows. We turn something on, we wait, then we turn something off, and then we wait. And so if we look at what that's going to do to the signal here, it's going to provide us this pulse width modulation, or this pulse here that has a on-off based duty cycle based off of this equation here. So duty cycle is how it's the ratio of high over the total period. So how is your average power? How long are you staying high? That's going to be your duty cycle. And the period, this period here stays constant. So period right here, we can see that high, low is constant. And then we manipulate how long it is high. So if I wanted let's say our period is 10,000, and I wanted a duty cycle of 75%, then I would keep it high for 7,500. And we can just say these are in microseconds, because that's that, we're going to create that 1 microsecond timer. So if my period's 10,000 microseconds and I'm high for 7,500 microseconds, that is a 75% duty cycle. And there's a lot of good uses for duty cycle. We saw it a little bit in 210, where we are creating the signal for our motors, and we're going to see that again here in 382. So if I take actually let's just move on to we're going to jump down, since I mentioned it, down to the applications of pulse width modulation. So let's talk about transfer power to control motors. So if I push in a pulse width modulation signal into one of our motors, what's going to happen is we're going to create this average power. So if I'm high, low, like that, that's going to relate to a higher average power and faster motor spins. If I'm high for a shorter amount of time, again, remember that period stays constant, even though this might not look exactly constant. Now this is going to correlate to a lower power, high average power, low average power. And this is going to be faster, slower. All right, so what we can do with this pulse width modulation, while keeping these periods constant, we just manipulate that high time, and we have a higher average power or lower average power. In the lab, what we're going to do is we're going to see that with the LEDs, because you think digital signal 1 or 0, on or off, LED is going to be on or off. But if we use pulse width modulation to create that average power, what's going to happen is it's going to be brighter with a higher average power and dimmer with a lower average power. And that allows us then to control the brightness of the LED. We can transfer or control the power of the motors. And the last thing is digital analog converter. You're not going to implement this, but I will have a demonstration during the lab. But this is still an important concept. So basically what we're going to be able to do is by sending a digital signal out with the low pass filter that's based off this equation here that you've seen in probably ECE 215, if not any other, some of our more digital classes along those lines. And what's going to come out is a analog signal. This is a very basic digital analog converter, but it is going to provide a pretty good analog signal. And we'll see this in the lab. We'll see this in the lab. And the important thing to note is, while all you're doing is sending ones and zeros, these are still digital signals. We're able to create this average power oscillation, almost analog signal, because of the duty cycle and changing that duty cycle to allow more or less power. Really cool stuff. So this lab, again, we're going to focus on the LEDs. Subsequent labs, we're going to actually implement this with the motors after the GR, unfortunately. All right, so let's just real quick talk about the code. I think that it'll be a little bit helpful, just kind of, especially when there's these programs that are in the labs, that I just kind of talk about what to expect from them, so that when you're in the lab, you kind of have an idea. Even though I write in, whether it's the comments or the lab write-up, what it does and what you should be seeing, I've noticed that some of you read probably every 10th word in the lab. So you get to the part where it says do this, and you've ignored pretty much everything else, which I will say will probably hurt on the GR. I will be doing a GR review for the next video, and one of the things I will mention is that looking at some of the background information on the labs will be very important for your success on the GR. But with that being said, I did want to talk a little bit about what the two test programs are doing for Module 9 lab, and then what you'll be implementing in your Program 9.3. So Program 9.1 and Program 9.2 both do pretty much the same thing. So the first thing you are going to do is you're going to create you're going to take, based off of this example here, which is similar but different, we're going to actually, and you don't have this with you anymore, you're just going to be loading something into a value into load, just like I explained it. You're going to create your wait 1 microsecond function. And then we're going to test that create 1 microsecond function here. with a very basic 75% duty cycle. And again, remember, duty cycle equals high over high plus low. So it's going to be on for 7,500 microseconds, and then off for 25, so low for 25,000, or sorry, 2,500, 7,500 microseconds, 2,500 microseconds, for a total of period of 10 microseconds. So remember, this is your period down here, and that's going to equal 75%. And it's going to show us an LED at 75% power. It's not going to be on. It's going to be on and off, but it's going to be so fast you can't see it. So that's going to create that dimness. So it's going to create a LED at 75% power. And then we're going to do the same thing, but we're going to use this kind of different format. This format here allows us to use these two very nice variables here, H and L, high and low. So 10,000 again is our period. We have our high time, and if we take our period minus our high, it's always going to be our low, right? Period, high plus low. So if I know my period and I know my high, I just use that then to calculate my low. And that allows us to then change just the H to our different duty cycle that we'd like. So if we wanted a 50% duty cycle, H equals 5,000. If we wanted, a 25% duty cycle, H is 2,500. And we'll see this once we get to the motors. We'll have different values so that the motors will spin up quicker and then go slower. So play around with that a little bit, see how your LED changes dimness with those different duty cycles. And we're actually going to bring in the logic analyzers again, and we're going to take a look at make sure our duty cycle is what we expect it to be. The last thing we're going to do is in this lab file, there's an array of duty cycles. Whoa. I think it's called pulse buff. So it's an array of duty cycles, pulse buff. And we're basically going to go through kind of this portion here, and we're going to change the duty cycle through this pulse buff array, and that's going to allow us to go from a very dim LED to a bright LED to a dim LED to a bright LED. And we're going to use a couple buttons to activate it and deactivate it. Again, this is going so fast that we can't see the on and off, but we can see the average power result. Same thing with the motors. The motor is not going to go on, off. That's theoretically what's going on with the digital signal, but what's really happening is an average power is being applied to those motors to create that slow to fast speeds. All right, that's it for Module 9 Note Taker. The pre-lab is going to be very basic. It's going to actually be implementing this wait 1 microsecond function. That's it. I know the GR is coming up. I want to give you guys enough time to prepare for everything. Plus, I want to get everything graded that's prior to the GR so that after the GR, everyone has a good idea of where they are. And so I just want to keep that pre-lab pretty easy. So again, next lesson is the SysTick timer. There's going to be a GR review provided to you via the video that evening, and then the following lesson, so next Wednesday and Thursday, is going to be the GR1. All right, that's all I got. See you guys.